Hello everyone! In this lesson, we will continue to study the frequency domain analysis module of continuous system. Today, we will study the characteristics of the distortionless transmission system. The main contents include the concept of distortion, the concept of distortionless transmission, and the frequency response function of distortionless transmission system. Let's start with the concept of distortion. In general, a system has two rules for signals. One is signal transmission, and the other is filtering. When transmitting a signal, system should keep the signal undistorted as much as possible. And when filtering, system should filter out or weaken the unwanted components, which is accompanied by the signal distortion. Figure 1 is an RC circuit. Let's take a look at its input signal. The input signal is a rectangular pulse, and its output waveform is shown in Figure C. Compared with the input signal in Figure A, the output signal in Figure C has a big distortion. Here we can find that the RC circuit is a linear system. It produces distortion in the process of signal transmission. Well, for linear systems, what are the factors that cause signal distortion? On one hand, amplitude distortion causes signal distortion. If the amplitude of each frequency component attenuates in different degrees, the signal will be distorted. The second factor is phase distortion. The phase shift generated by each frequency component is not proportional to the frequency, so that the relative position of each frequency component of the response on the time axis is changed. Therefore, it causes signal distortion. So, the distortion of linear system is actually the change of amplitude and phase, but it doesn't produce new frequency components. While the linear system will produce nonlinear distortion, which will produce new frequency components. In practical engineering, the requirements of the system are different according to different purposes. Fidelity signals are required for undistorted transmission. The nonlinear system applies distortion to transform the waveform. Let's take a look at the concept of distortionless transmission. Distortionless transmission means that the output signal and the input signal of a system are the same in waveform, and their amplitude and occurrence time of the amplitude are different. This is its basic definition. Well, what are the input and output relationship and mathematical description of distortionless transmission system? If the input signal of a system is Ft, its output signal is Yt. According to the definition of distortionless transmission, obviously Yt should satisfy Formula 1. The amplitude is not same as the input signal. Occurrence time of the amplitude is delayed for a certain time, but their waveforms are the same. If they are denoted by their amplitude frequency characteristics, their spectrum satisfies Formula 2. Fj omega is the spectrum of the input signal. The output spectrum Yj omega is equal to k times e to the power of j omega Td times Fj omega. Here, there is a certain phase change. Let me show you the input and output waveforms of a distortionless transmission system. If Figure 1 is a distortionless transmission system, when its input signal is Ft, its output signal should be yt. Compare yt with ft. The amplitude of ft is 1/2 times of yt, and yt is obtained after ft is time shifted td units to the right. Let's discuss frequency response function of distortionless transmission system. According to the definition of distortionless transmission system, to achieve distortionless transmission, what are requirements of the system for ht and hj omega? First, let's look at the requirements for ht. The unit impulse response of the system should satisfy the formula 3. Obviously, according to the input and output relationship of the undistorted transmission system, the formula 3 is true. The requirement for hj omega is very simple. If we take the Fourier transform of ht, hj omega is equal to k times e to the power of minus j omega td. That is to say, hj omega should satisfy formula 4. Formula 4 can be further transformed to formula 5. This is its amplitude frequency characteristics. This is its phase frequency characteristic. Figure 3 shows the spectrum characteristics of a distortionless transmission system. As shown in Figure 3, for a distortionless transmission system, its amplitude frequency characteristic is a constant, and its phase frequency characteristic is linear. The content discussed above is the ideal condition of signal distortionless transmission. A signal with limited bandwidth can be transmitted as long as in the frequency range occupied by signal, the amplitude frequency and phase frequency characteristics of the system meet the above conditions. For example, an ideal low filter can be regarded as a distortionless transmission system, as long as the phase is proportional to frequency of the system. The system can transmit signal without distortion. That is to say, the phase characteristic curve must be like that, as shown in this figure. Only when the phase is proportional to the frequency can each harmonic has the same delay time. That is to say, only when the delay time of each harmonic is the same, the superposition of each harmonic can be undistorted. The delay time Td is the slope of the phase characteristic, as shown in Formula 6. Usually, Formula 6 is denoted by Formula 7. Tau is called the group delay. Obviously, the group delay of the system should be a constant under the condition that the signal transmission does not produce phase distortion. Here is an example of distortion. In this system, the input signals are sin t and sin 2t. If sin t and sin 2t are superimposed, we can get such a waveform. Input these two signals to the system. The time delay of sin t generated by the system is t minus 2, and the time delay of sin 2t generated by the system is 2t minus 3. Here, the actual time delay of sin 2t is 3/2 units. And for sin t, the delay is 2 units. Obviously, the time delay of the original signal sin t and its second harmonic are different. So after passing through the system, the output of the system becomes such a waveform. Compared with the waveform of Figure A, we can find there is an obvious distortion. The system does not satisfy the phase characteristic of distortionless transmission because the group delay is not a constant. The signal can also be simulated by software. The ideal low-pass filter mentioned above is a local distortionless transmission system. Now, I will introduce to you the concept of filter, ideal filter, and ideal low-pass filter. But what is filter? For a system, if the frequency response function Hj omega can allow signals with different frequency components to pass and it can stop some of them passing, then the system is called a filter. The ideal filter refers to a system that can filter out all of the frequency components that are not allowed to pass, and can allow all of the allowed frequency components to pass it smoothly. Obviously, in the ideal filter, the amplitude and the phase of signal in its passband are undistorted, and the frequency components in stopband are attenuated to zero. There is an obvious boundary between the passband and the stopband of the filter. In other words, the amplitude frequency characteristic of the ideal filter in the passband should be a constant, and the slope of the phase frequency characteristic should also be a constant. The amplitude frequency characteristic outside the passband should be zero. This is the concept of the filter. As for the content of ideal low-pass filter, I will give you a further explanation in the next lecture. In this lecture, we learned about the concept of distortion and the concept of distortionless transmission system and its frequency characteristic. The amplitude frequency characteristic is a constant. Phase frequency characteristic is a linear function. Therefore, the time delay of signals with different frequencies generated by the system should be the same, and the group delay of the system should be a constant. So much for today. Thanks for your listening. Goodbye.